Welcome back to the Narrative Monopoly podcast. On today's episode, we have Jason Crawford, the author of The Roots of Progress, a site that talks about the history of technology, industry, and the philosophy of human progress. Jason is definitely one of the smartest guys I've ever spoken to. I asked him a wide range of questions, and he had a thorough answer on every last one of them. He definitely knows what he's talking about when it comes to progress and what is progress, which I ask him right off the bat, how he studies it. So some of the things we go into are vaccines, specifically the new technology developed in mRNA. We talk about regulatory structures and how it affects progress, funding models and progress, how much money it would take for you to go back to when Rockafeller was alive. I'll save the answer for that later in the podcast. We also talk about the Great Stagnation and space factories, which you're going to have to listen to find out what that is all about. All right, well, this is episode number 2. Without further ado, let's press play. All right, Jason, thanks for coming on the program.
Yeah, thank you very much for having me. Good to be here.
I am excited to talk to you because I found you from probably one of the smartest yet funniest tweets that I've seen, which was basically that we've made a lot of progress, and we know this because we've progressed a lot with shit, with feces.
Yeah, that's right.
You are the author and founder of Roots of Progress.
Maybe we should give a little context for that one. I'll just say that I wrote that thread because I was doing some research for an article I'm writing, and I was just struck by how much excrement played a role in daily life for so many people in the city and the country for much of human history. And like, the fact that we don't have crap all around us all the time is is actually sort of new and unprecedented in history. So I just thought that was an interesting, a thing that people don't usually think about.
No, I think that, there's so many things that people don't think about, right? Like there's everything from energy, medicine, housing, all of that stuff, which we'll get into. But yeah, so I think that that's the thing that really made Roots of Progress stand out. I also found you via the fact that you are a consultant to Our World in Data.
Yeah, that's right. I do some technology consulting with them and work with that team. It's a great team and a great website.
When you're working on figuring out what is progress, where do you start? Like, how do you define what is progress?
I think of progress in a broad sense as anything that helps us live longer, happier, healthier lives, more thriving and flourishing, more choice and freedom. And, so a lot of what we talk about when we talk about progress is sort of technological and economic material progress. And sometimes when people say progress, they're really just thinking about that kind of narrowly. But we've also, of course, seen a lot of progress, especially in the last 500 years or so, in science, knowledge, and the expansion of our understanding of the universe. And I really think we have seen a lot of progress over human history also in morality, society, and government. This is what Steven Pinker's book, The Better Angels of Our Nature, was largely about: the decline of violence in history as one major aspect of that, not the only aspect. And so I think of, all of those things as progress. I think the improvement in material life, in economic progress and technological progress, I think is kind of the most obvious and undeniable, with, the progress in science maybe being right up there or close behind. I think progress in morality and society is harder for people to see, and maybe it's been even messier. All progress is messy, but social progress is seems like the messiest of all. the one where there's the most kind of 2 steps forward, 1 step back. And so it's hard for people to see, but I really think it's there. I think Better Angels gives a lot of evidence for, for, like I said, one aspect of it, the decline of violence. In Pinker's subsequent book, Enlightenment Now, he gave a number of other examples of, ways in which there's been progress as well on the social level. So I really think we see progress across the board if we look across a long time span of, say, a few hundred years, or up to at least 500 years or so.
So it sounds like basically you're bifurcating progress into material wealth and also the well-being of us as animals, basically, and then also the way that we organize and treat ourselves amongst each other, right?
Yeah, and you could maybe add in knowledge and science as a third category. So think of it as like material, cognitive, and spiritual or moral, perhaps.
And so when you're studying this, with the roots of progress, are you looking at it through those three lanes, or do they all kind of filter to the same place?
Ultimately, the story of progress is one story, and those three areas of progress are all intertwined and interdependent. I don't think you can fully understand human progress without understanding all of them. In most of my work over the last couple of years since I started this project, I've been focusing on technology and material progress. That's sort of my current focus. I think it's the most obvious place to start. But I'm very interested in the other topics as well, and I've done a little bit of reading and writing on them.
So let's start with science. And this mRNA vaccine is just an incredible achievement for mankind and how quickly it was done, right? So I assume that this is something that you've been working on. What does this mean in terms of the speed that we can develop drugs and cure diseases? Assuming that that's a central tenet, it sounds like, of what you're studying in progress.
Yeah, absolutely. I mean, to put this in context a bit, yeah, vaccines often take decades to develop, measured from the time that we identify the pathogen, the virus or bacterium or whatever that's causing the disease, to the time that a vaccine is ready for the public. I think the fastest before this was about 4 years. And now we have done it in less than a year with not just one vaccine, but multiple. And so that is unprecedented progress. It is huge. And part of why we were able to get there was this mRNA technology that lets us design and manufacture vaccines using essentially a fairly generic platform. That the great hope is that this could then be rapidly deployed against many other types of diseases. To give just a brief, for people who don't know what the mRNA thing is all about, or how vaccines work, just give just a very brief overview of kind of the 300-year history of vaccines. It was recognized very early on, in particular with the disease smallpox, that if you got it once, you would not get it again. And so people sort of knew that since ancient times. Sometime in the Middle Ages, probably in China or so, a folk practice began to emerge, which was actually deliberately giving people a mild form of smallpox in order to grant them that immunity. Right? The idea was, look, if everybody gets this sooner or later, pretty much, especially in dense cities, if you're gonna get it, why not just do a mild case early and kind of get it over with, right? Like you have to do it sometime.
I got chickenpox when I was a kid.
Exactly, right. So there was this folk practice called inoculation, where they'd actually give people smallpox. And this actually spread. So before we had any vaccines, this practice actually spread from China and India, where it probably originated twice independently, ended up spreading through the Middle East and then to the West, to Europe and to America in like the 1700s. And cool. So this was essentially the first, proto vaccine. The big breakthrough after that was when somebody realized that you didn't actually have to use smallpox in this procedure. There was another disease, specifically cowpox, that was even milder, but would give like cross immunity, right? So you could repeat the same procedure where you give people a mild case of the disease, but instead of using smallpox, use the cowpox vaccine, virus rather. And it was Edward Jenner who discovered this and made it work at the end of the 1700s. And so that is, he called it a vaccination effort and or technique rather. And, that's where we get the term from. It wasn't until almost 100 years later that we were able to apply this technique to any other disease whatsoever. So for the longest time, the only disease we could use this technique against was smallpox. It was only after the germ theory was developed, and especially through the experimentation of Louis Pasteur, that we figured out how to make vaccines against other diseases. Essentially, what's going on in a vaccine.
Is that the same guy that invented pasteurization? Is that where that comes
from? Yes, absolutely. Yeah, it's named after him. Yeah, so he was one of the pioneers of the germ theory, along with the German Koch. So Pasteur and Koch pretty much are kind of the two leading lights of the germ theory in the 1860s through 1880s or so is kind of when that's getting established. And they and Pasteur, in experimenting with different diseases, accidentally discovers a way to grant immunity. Essentially, what's going on here is that when you get a pathogen, some disease-causing particle, virus, bacteria, whatever, fungus in your system, your immune system develops antibodies against it. The first time this happens, it happens slowly, too slowly for you to fight off the disease, perhaps, right? But future infections, because you have certain memory cells in your immune system, future infections can deploy these antibodies much more rapidly. And so that is essentially why you don't get the disease twice, because after you've seen it once, you have these memory antibodies. So the whole point of a vaccine is to give you those memory cells, that memory to your immune system, without actually having to go through the disease. So the whole thing started out with you could only you got only a mild case of the disease. You suffered a little bit, but it wasn't, generally wasn't life-threatening. That was the original smallpox technique. And then by the time of Pasteur, he is able to actually modify the viruses and the bacteria themselves, either weakening them in a way such that they can't cause a full-blown disease in a human, or inactivating them, quote unquote, killing them, typically through chemical means or through heat or air or whatever. And so for a while, these were the two main vaccine techniques. You had this attenuated, and then you had attenuated is the same as weakened, right? Or you had killed or inactivated. And many new vaccines were made on this principle. Pasteur, the first one he developed for humans was for rabies. We got a number of other ones, famously for polio, influenza, both in the middle of the 20th century, et cetera. But even these attenuated and killed vaccines, they still had risks. An attenuated vaccine had the risk that it was actually a live virus or bacteria. I'm not sure whether this was done with bacteria. It certainly was done with viruses. A live attenuated virus vaccine is one that actually does replicate within the body. It just doesn't replicate very fast. It's not optimized, evolutionarily optimized to replicate within the human body. So you fight it off before it causes disease. But if it mutates, it can mutate back into a virulent form. Similarly, if you have a killed or inactivated virus, that's not going to do anything to the body because it's actually been chemically, inactivated, unless something goes wrong with the inactivation process, in which case, the manufacturing process for the vaccines, in which case you could end up with virulent, with a vaccine that actually gives you the disease, exactly what you're trying to prevent. This actually happened in the early days with polio. One of the, I think, 3 companies that was manufacturing the initial polio vaccine was using a process that was not perfect and ended up incompletely killing the virus particles. And some children tragically got polio from the vaccine. So there were real risks. A technology that came along in the late 20th century that makes this better is what's called subunit vaccines. Now, instead of using the entire pathogen, the entire virus or bacteria or whatever, you can use just a piece of it. So this is what happened with the coronavirus vaccine. Everybody's seen the pictures of the spiky ball, well, the spike protein itself, just the spike, is enough to generate an antibody response. And so basically the way a subunit vaccine works is it takes a piece of the virus, like the spike, and puts just that piece in your body. Now your immune system still attacks it and forms memory against the spike. When the actual virus shows up with spikes on it, your immune system is ready to attack it. So subunit vaccines were used ever since the late 20th century. I think the first was in the 1980s or so. What's new about the mRNA is really the speed of design and development of this kind of vaccine. So the mRNA vaccine for COVID that targeted the spike protein, it is a subunit vaccine. It is putting the spike protein in your body, but it's doing it not by having to manufacture the spike protein in some sort of a biological factory and then putting the spike protein in vials which we inject into people. Instead, it prints the RNA code for the vaccine, and it injects the RNA itself into your body, and your body becomes the factory. Your body becomes the factory to make those spike proteins simply by injecting the code into it. And from there, it works just as if we had injected the spike protein itself into your body, essentially. Your immune system recognizes it and forms the antibodies. So this is a breakthrough for, genetic engineering. I mean, this technology has been worked on for a while, but this is the first time that an mRNA vaccine has actually been approved for general use. And we can see the amazing, potential. Most of the, 9, 10, 11 months that it took to go from identifying the new virus to having the vaccine ready, almost all of that was clinical trials and other testing and development, right? So the trials are now the bottleneck, and the ability to very rapidly design and develop something. They didn't even need to possess or manipulate the virus itself within the laboratory. All they needed was the code. The code was originally sequenced, I think, in China. The virus was, its genome was, and from that they were able to pick out the part that they wanted to, basically put into the vaccine. So, it's a breakthrough, and the big hope is that we can use this to very rapidly develop vaccines for other known diseases, and also very importantly for any new unknown novel diseases that crop up in the future and cause new epidemics.
Do you have any sense of the safety? Because I think that's on everybody's mind, right? Is like, if this is a new, people just think, okay, if this is new, then maybe it's not tested and not safe. I just got a text today from a buddy that said, well, I don't know what it's going to do to me in 5 years. So is there any sense there on the safety factor of this?
I mean, from what I understand, look, all of these vaccines go through a lot of development and testing, right? I mean, I've only read the details on the Pfizer BioNTech trial, but they recruited something like 40,000 people for that, right? So tens of thousands of people have gotten this. If there was something that was going to show up a significant number of times, we'd have seen it by now. And I don't think there's been anything significant at all. The biggest in general, there with vaccines, there is a very rare thing that does happen where somebody can have an adverse reaction, to the vaccine. My understanding is that happens to 1 in every several 100,000 people, close to 1 in a million or maybe 2 in a million. It's extremely rare. If this is the sort of thing that you personally are subject to, you should find that out and be concerned. But it is not something for people in general, to be concerned about. And then, the other thing with vaccines, historically, like I said, a risk has been if they weren't properly manufactured or something, you could actually catch the disease itself. That cannot happen from a subunit vaccines because it is not, you're not putting the entire, pathogen, even in a weakened or killed form, in the body at all, right? You're only putting one protein. There's a protein on its own cannot replicate, right? It takes genetic material in order to replicate.
Right. Look, my personal opinion on this thing is that the generations before us, these guys my age, if they could storm a couple beaches, then I think I can take a vaccine to help out the country. I think
I
one
think, I mean, I think
important
it helps yourself, right? I mean,
that's
I mean,
true.
I'm interested. I want to get the vaccine for very personal, selfish reasons, right? It'll because I want the immunity it'll give me, right? I think pretty much
Oh,
everybody
absolutely.
should. I think it's a pretty straightforward trade-off.
So you hit on one point about how the testing has become the bottleneck, and I want to read a piece from. I found this from a Ben Thompson article, but it's from a New York Magazine article, and it says you may be surprised to learn that the trio of the long-awaited coronavirus vaccines had been designed by January 13th. This was just 2 days after the genetic sequence had been made public. I'm skipping over a bunch because it's a little long here. But it was completed before China had even acknowledged the disease could be transmitted from human to human, more than a week before the first confirmed coronavirus case in the United States. By the time the first American death was announced a month later, the vaccine had already been manufactured and shipped to NIH. So what gives? Why are we waiting so long?
Yeah. So first off, vaccines do need to be tested, right? It doesn't make sense to just sort of take something hot off the presses, so to speak, and then start distributing it to everybody in the world. Our testing procedures, I think, were designed in a world where it takes years to develop a vaccine, right? If it takes years to develop a vaccine, spending one more year testing it maybe, is not too much of a burden. If we're now in a new world where where a vaccine can be designed in days or weeks and developed, I mean, there's more than just the immediate design process. There's there are more steps to it. But if it can really be developed that fast, then it is at minimum time to rethink our testing processes, right? I think it's definitely time to ask, okay, great. If testing is now the bottleneck, is there a better way we can do testing? One thing that was advocated by a number of people, including prominent epidemiologists early in the pandemic, was the use of human challenge trials. This is to back up and explain that a little bit. The way these trials were done, they gave the vaccine to tens of thousands of people, gave an roughly equal number a placebo, and then told them all to go about their lives and report if they got sick. Then, they count up, okay, how many people got sick and how many of those came out of the control group versus how many came out of the vaccine group. This takes a while, right? It's not like, so contrast this with a trial for a drug that is meant to cure a disease. You give it to the people who have the disease and you see if they get better. If you're expecting that to happen quickly, all of the people, that you are in the trial are going to have the disease, right? And then hopefully you can rapidly tell whether they're getting better or not. But in a vaccine trial, the design the way I just described, first off, you need to recruit a much larger number of people to get to statistical significance, right? Because a lot of people are not going to be exposed at all. And so they, effectively aren't giving you information, right? And then you have to wait a while. You have to wait several months for all of this to happen, right? In a certain sense, it's there's an almost perverse trade-off here, which is that the more the pandemic is actually tearing through the population, the faster the trial can conclude. So in fact, if we had done maybe a better job of social distancing and whatnot, it might have taken even longer for the trial to finish. So a human challenge trial, in contrast, says, okay, look, we are going to take a set of young, healthy volunteers who are in the lowest risk group for this virus, and we are going to deliberately expose them to the virus. So we're going to have our placebo group, our control group, and our treatment group, and we are going to give the treatment group the vaccine, and then we are going to expose all of them to the virus, and we will see how many of them in each group get the disease. Okay. Obviously, now you are putting, these are volunteers who are stepping up to be put at risk. Worse, half of them are not even getting a vaccine before they get exposed, right? You need the control group to know how many, right, to see under these conditions of exposure, how many people are getting the virus.
That's
So
in
you
the
can
challenge
expect that
trial.
virtually, this is in the challenge, I'm now describing what is known as a human challenge trial. Yes. So the challenge is you actually expose them to the virus. So you're basically getting a bunch of people stepping up to be, and that many of them, virtually all of them, you presume in the control group will get, will actually develop the disease, or a significant fraction of them. And then it's even worse than this, because how do you know what level of the virus is sufficient, what level of exposure is sufficient, and what process is sufficient to actually create the disease in people? Well, there's a previous phase where you do where you determine that, and you do it by exposing another set of volunteers to gradually higher and higher levels of the virus until you can reliably generate the disease. So you got to get a bunch of people who are willing to step up and sort of put themselves in harm's way, as it were. This is really like, recruiting soldiers for a war, right? There are obvious, serious ethical concerns about this. And yet, I think you can, and I think some people did back in March, April, May sort of time frame, make a serious, sober, thoughtful, ethical case that this is the way to do it, because it can rapidly accelerate these vaccine testing timelines. This was not done. That is just one idea. But I definitely think we're at the point now that this has been demonstrated, it's time to start thinking about the next bottleneck, right? How can we do better at testing so that we could we have started rolling out this vaccine 6 months ago, if, given the right testing procedure? I'm not saying that, necessarily we should have absolutely done that in the beginning. But I absolutely think now that we've seen what this last year, looked like, if the people in charge of pandemics, don't start thinking about how can we improve our testing procedures to have rapid vaccine approval in the future, then they're just, they're not doing their jobs.
Yeah, I mean, the challenge trial thing, it doesn't seem controversial to me, because if we're paying someone and they're an adult and they make that decision, how is that any different than bungee jumping, or, as you said, being a soldier? If you're going to join the Marines, I don't understand how that's a controversial thing. I guess is this, is what you're describing, is the problem more of an FDA thing, or is it the fact that this is a new technology in mRNA that we're using here?
I think it's the fact that you're deliberately exposing people to a dangerous virus, and yes, they're volunteers, and yes, they're being compensated, and you would do other things for them. For instance, you would keep them under close surveillance. You would provide the best possible medical care to them if they get sick, and so forth, right? Again, you would recruit them from the lowest risk demographic groups, right? So that, but, it's quite possible that there would be casualties out of this. And so I do think that you need to slow down a little bit and think very seriously about the ethical concerns. I still think at the end of the day, something like a human challenge trial, seems justified to me. And I think good cases were made for it, and I found those cases convincing. But it's certainly something you have to think through.
Yeah, I mean, look, that totally makes sense. I think just reading the statement that we had the vaccine, and obviously hindsight's 2020, and that vaccine could have been unsafe, could have not worked. But looking at it now, it's like, we had it the whole time. What are you doing? And now I think it's 350,000 people that are dead as we're speaking about this. Let's zoom out a little bit here. When we talk about progress and you talk about advancing what is these new technologies like mRNA, does it have to do with, as we just talked about, kind of the regulatory structure? There's also the funding structure. I've read a lot about how this specific practice came to be, that we developed these vaccines. but I have no idea, what is that? Where did the money come from to do that? Who was it? Was it academics in universities? Was it corporations? And who was actually putting up the money for that? Was it government grants? I feel like there's a lot of pieces to this puzzle, and how we unlock this stuff. And I know that's what you've been working on. So how do you think about that in a more comprehensive sense?
You touched on a couple of key points. I think in terms of, looking for levers where we can improve progress and accelerate it, I think about a few different things. So one, you mentioned funding. I do think that looking at how we fund progress is important. I think we have a variety of funding models today, and I'm not sure that they are all, that they sort of cover all the bases, so to speak. We have, anything that can be, anything that can quickly turn into a profitable business, and by quickly I mean within, say, 10 years or so, and can serve a large market, can generally be, kind of funded through for-profit, private funding sources, venture capital, and so forth, right? Other things are typically done through, especially kind of like long-term things like research, frequently done in universities and private private or public research labs, funded by both private and public sources. Government funds a ton of research. There are also a number of foundations. But there has been a case made by a number of people that the way that we fund research today has become overly centralized and bureaucratic. And because of that, it's slowing things down just in terms of the amount of time and overhead that goes into, say, grant writing. And perhaps more importantly, that the process lends itself to a kind of consensus and groupthink, especially since so much of it is done through committee, peer review. And that this kind of mechanism is the kind of thing that can kill breakthrough ideas in their very early phases, when they go against kind of the status quo or established, ideas or doctrine. So I think that, finding ways to reform and improve funding, especially of science and research, is a big one.
Where are those choke points? You're talking about peer review. Are we talking about government, academia, or even in corporations, or these partnerships? What is you're talking about, like there's a bureaucratic kind of backlog here. Where does that get reformed?
A good question. And I mean, part of the question is, do you want to reform it, or do you want to sort of, work around it and provide alternatives? The sort of committee-based peer review that I was talking about, primarily I know of it being at the NIH and NSF, right? This is kind of how a lot of those federal grants for research are done. I know less about the processes that private foundations use, the Gates Foundation, for instance, if they're going to go and support research. But private foundations are I think a relatively small, they're a minority of the overall funding. Anyway, NIH is huge. NIH is about $40-some billion a year. It is the largest funder of life sciences in the world. It is the federal government, I think, funds more than half of university life science research. So it's fairly dominant, right? And you kind of, if you're a life science researcher, like I think you're in the US at least, like you're gonna be going for NIH grants, right? So I think you kind of, I think that's a place to start.
That all makes sense. Well, let's talk about the corporate side. AlphaFold. I'm hearing, this is something that has not made a ton of noise. Think about the mainstream news outlets, but from the people who have spoken about it, it sounds like it's just an earth-shattering breakthrough. So this is at Google, right? And they figured out how the protein folding problem works.
Yeah, it is a breakthrough. Yeah, so I mean, just to explain that briefly, proteins are these really complex molecules. They are long chains of, what are called amino acids, but they fold up in these really complex and non-random ways. They actually fold up in very definite ways to form complex shapes. You can think of it essentially as like a protein is like a self-assembling nanomachine. And after it is printed, quote unquote, by your RNA mechanism, protein expression mechanism in your cell. It's this long string of amino acids, and then it just kind of, via physics, folds up into this sort of complex globular shape. We know from DNA sequences, from that we can determine the sequence of amino acids that makes up any protein. But what we don't know from that is exactly how it's going to fold up and what shape it's going to be. And understanding a protein's shape is essential to understanding its function. So historically, these shapes have been determined through experimental methods, the number one being X-ray crystallography, which is a general method we can use to find the structure and the shapes of large molecules. But in recent decades, we have also tried to put computer power against the problem to see if we can predict or simulate this process and just predict what shape a protein is going to fold up into. It's an extremely computationally intensive problem to do in any straightforward way. Any way you might think of approaching it just requires an enormous amount of time on the most powerful computer systems that we have available. Google DeepMind came up with a way to approach this using deep learning techniques from artificial intelligence, machine learning techniques. And they have been able to get, in the most recent competition, they were able to get results that were in the range of the experimental accuracy for the first time ever. It had hovered at, things had hovered at the best techniques had hovered at, I forget, 40 to 60% accuracy or something for many years. And then, AlphaFold has been able to get it up to 90% sort of accuracy range. So yeah, that's a breakthrough. And I think, is one more piece along with mRNA vaccines, along with CRISPR and so forth, that I think could become the building blocks, the fundamental tools of, a real revolution in genetic engineering over the coming decades.
And what would that mean for humanity? Why is AlphaFold or CRISPR? Why are they so important? We talked about mRNA earlier, but why are the other two, specifically AlphaFold, why are they so important? What's this going to unlock?
Well, I mean, we're made of cells and they are programmed by DNA. Also, every, our pets, the food that we eat, the diseases that we encounter, all of it's biological. So what if we fully understood, or, what if we had an ability to manipulate biology the way today we can manipulate chemistry? In a steel plant, the alloys of metals that are created can be, created with accuracy to the, 100th of a percent in terms of the mixture of metals, right? We can get things with these exact properties. We are so far away from anything like that when it comes to biology, right? All of our drugs are these blunt instruments, and we don't even understand how they all work. Cancer. I mean, think of how we treat cancer today. We zap you with radiation, or we poison you with chemicals, or we cut a piece out of your body. I mean, these are the best techniques. So, imagine that we had mastery over the biological world the way we, to the level that we can control the chemical world. That would change the lives of everybody on the planet, right? We could, you can see this being the path to curing cancer, to understanding and ultimately curing all disease, to possibly, ultimately to understanding and curing aging, to really extending human lifespan and health. You can see this as the path to optimizing food production and nutrition. There's just all sorts of things we could do. Now, I can't claim now that nobody can see the exact path to how that's going to happen, but it seems fair to assume that, a fundamental understanding of an ability to manipulate the code of life is just a key, pathway to all of those kind of possibilities.
It is pretty incredible to think that we're living through it right now. As you mentioned earlier in the conversation, it's really only the last 500 years that we've had this extreme acceleration. I want to switch gears here for a second and kind of give you a little bit of a challenge. What year would you have to go back to for the richest American to live an equivalent life of the poorest American today?
It's sort of impossible to answer because progress is a multi-dimensional thing, right? So if you look at somebody I'll just point people to an article. There was an article put out by the Foundation for Economic Education, FEE, about John Rockefeller, right? John D. Rockefeller, who was like the richest person at the time, or the richest businessman at least. And they described his life and the things that he had and the things that he didn't have because it hadn't been invented yet. And it sort of posed the question, how much money would you have to be paid in order to be willingly sent back in time to Rockefeller's era? And if the answer is not, if the answer is something greater than Rockefeller's actual wealth at the time, then there is a sense in which, you today are richer than Rockefeller was in his time. I mean, one of the more powerful, and certainly ambitious kings who ever lived, like Louis XIV of France. I believe, I may be remembering this incorrectly, that he contracted smallpox. People in that era still, even kings didn't have central heating, right? they were shuddering in the cold at the dinner table, right? And then they had to go by the fire to heat up. He didn't have, toilets, right? I mean, he, peed in a chamber pot, or I read in one place, even in the stairwells of the palace, and so forth, right? So the greatest, kings and emperors and pharaohs and rulers of the ancient world, there are things today that almost anyone can do that they cannot, right? Listen to recorded music, listen to the greatest performance by any artist anywhere in the world that that has ever happened and been recorded, right, on command. Get a message halfway around the world instantly, right? Communicate with friends and loved ones who are far away, etc. I mean, I could go on and on. But that is, so there are now, it doesn't mean that there aren't people in the world today who are worse off than the kings of old. There are some. There are still people today living in extreme poverty. There are people that a lot of the progress, that we've made hasn't reached them. But the incredible democratization of wealth, when you measure wealth in real terms, in its ability to enhance human life, in terms of standard of living, quality of living, that democratization of quality of living is really considerable, is really amazing. Now is the best time to live.
Yeah, I mean, I think even an anecdote like Calvin Coolidge's son dying while he's in the White House because I think he was, mid-20s, and he stubbed his toe playing tennis, got an infection, and died, before there was penicillin. I mean, that's only 100 years ago. It's the president's son. But, you make a good point around that. It is, it is an incredible democratization of wealth, and it hasn't reached anyone yet. I think, I'd like to hear your thoughts on this conversation that I'm sure you're familiar with, of if we are living through a great stagnation. Is growing horizontally, which essentially what globalization is, the more wealth that is going to every corner of the world. I mean, does that count? It obviously counts to those people, but it's not the same as we think of it in terms of, the stories we tell ourselves, and in the fact that, 100 years ago, you could not fly all the way around the world, and now you can fly anywhere that you want. And those leaps and bounds at least to the naked eye, seem like they're slowing down. But I know there's a lot of argument on both sides there.
The stagnation hypothesis, or referred to as the Great Stagnation, is about science, technology, and economic development in the US and other wealthy countries. And on that front, I do think there has been a slowdown of progress in the last 50 years or so, since about, say, 1970. A slowdown of progress, note, is not zero progress. I think the rate of progress over the last 50 years has still been high by long-term historical standards. It's still high, certainly compared to the Middle Ages or the ancient world, or anything before about probably about 1700. But it's not. It seems to be not quite as high as it was in the late 19th and early to mid 20th century. And a simple way to see this, and to my mind, the most compelling way to see this, you can look at quantitative factors like GDP growth and so forth. That will show you something. GDP growth certainly is slower. A number called TFP, which stands for total factor productivity, which is a component of GDP growth that is supposed to be, that is attributable to, technology improvement and process improvement and so forth, is also lower. There's a lot of debate over those numbers. Those things are very difficult to measure and so forth. I actually find it a little more compelling to look at it in a more qualitative sense, as follows. If you just look across all the major areas of industry, manufacturing, construction, agriculture, transportation, information, energy, and so forth, and you just ask, look, how many of these major areas were being fundamentally revolutionized? Well, in the late 19th century and into the early 20th, there were something like 4 or 5, by my count, major revolutions all going on at once. So we had the oil industry being developed, and along with that, the internal combustion engine and cars and airplanes. At the same time, we had a second fundamental revolution in energy, which was electricity. And that industry was getting built out. We had electronic communications. So the telephone was invented in 1876, and then radio and television in the early 20th century and so forth. We had synthetic chemistry creating things like new pharmaceuticals, synthetic fertilizer, the first plastics, et cetera. And we had the germ theory getting developed in medicine, as I mentioned earlier, and getting rolled out and applied in new vaccines, in water sanitation systems, in public hygiene, efforts, and so forth. All of these things are going on at once. Essentially, every major area of the economy had some enormous, fundamental revolution that was transforming everything, all at the same time, all in a span of, about 50 years or so. In the last 50 years, the only thing that we've really had that's been at that level is the computer and internet revolution. Now, the computer and internet revolution is nothing to scoff at. It's huge. It's enormous. It's a complete transformation within one industry and one alone. Now, and of course, it has ramifications and echoes and impacts on every other industry. But that was true of all the previous revolutions as well, right? And they were all going on at once. So computers and the internet, absolutely huge. But I think the computer revolution is roughly, equivalent in magnitude to any one of the 4 or 5 things that were going on at the end of the 19th century, right? The computer revolution is roughly equivalent to electricity, or to, synthetic chemistry, or to, electronic communications, right? The early electronic communications, et cetera. But it is not equivalent to all of those added up together. And there really just hasn't been anything. I mean, there's been certainly we've seen the beginnings of genetic engineering, but we haven't really seen that come to full fruition, right? I think that's still in the future. And then when you look across, well, what are some of the areas maybe where it seems that there wasn't so much progress, and what could have happened or should have happened or started to happen and didn't? Well, in aerospace, we got the first supersonic airplanes, but they were always really kind of a luxury for the rich. They were never made affordable, and then they were shut down, and now we don't have them anymore. And now private companies like Boom are coming along to try to, bring that back. in a much more affordable, way for a broader audience. Similarly with space, right? We had a rocket program, we had the moon mission, and then we let it drop. And now again, private companies are sort of, trying to bring that space capability back. In energy, we were supposed to have a nuclear revolution. Nuclear power was supposed to, bring all of our electricity, make it too cheap to meter. It was, it was going to really transform the world, and then it didn't. Nuclear power is, I forget, something like 10% of world electricity today, and so forth, right? So you can kind of look across all these areas and realize that there were things that people at least thought were going to revolutionize them and then didn't. And so again, really the only one that came to full fruition and is at all comparable to those revolutions of hundreds some years ago, is computers and the internet. I think if all of those things had been going on at once, or at least we'd gotten 3 or 4 of them, right? I think then you could say, and I think we would also see in the numbers and the GDP statistics and so forth, that this era that we just lived through was, that there was no stagnation, that this era was just as productive as the past. But we didn't see that. And so that's kind of the analysis that is most convincing to me that progress actually has slowed down a bit.
The ones that you mentioned with, NASA and supersonic airplanes and, the things that, we gave up on or got forced out, those hurt. Those hurt, right? I mean, it is kind of crazy that we went to the moon and here we are, 50 years later, and it's going to happen soon, right? I think it's called Artemis. Is that the one that they just announced, the moon landing? That'll happen in a few years. That's sad. And I think my first thought is that does that just go back to funding and how we think about these things as a society? Because not everything is going to be as easy as, writing a check into Facebook, and then it's a very easy it's not easy to do, but it's an easy path to follow of like, okay, we need to grow, then we need to monetize it, and the money's there, right? But these big, huge bets that actually have to do with things in the world of atoms, that those are the things where it's like, are we focusing enough time and attention on those? And I guess, my thought is, or my question to you is, how much are of those huge industrial projects that kind of fit into that category have to do with the outcomes of, what we're calling progress, right? Like, are those tenets of the world progressing?
So to take a look at the aerospace examples, I think, why did we end the Apollo program? Well, it's pretty simple. We conceived of it as a space race with the Soviet Union, and we won. And once we won, there was no need to keep racing. So we shut it down. The lesson out of this, I think, is that, it's a lot more likely for something to be sustainable if it is profitable, right? The surest way for something to be sustainable is if it has an economic model, behind it that makes it self-sustaining. And that's why I'm optimistic now about, about private space companies and about they are looking for actual economic reasons, to go to space in a way to make it, to make it profitable and self-sustaining. At least some of them are. And I think if it's going to happen, that's how it's going to happen.
Yeah, I think that what I was alluding to is really just time horizon, right? So those things that are profitable, I mean, they may not be. I think it's Varda is that company that is going to be, manufacturing in space, which sounds really cool. But you'd imagine that company is not going to be, generating a lot of profits anytime in the near future, right? So that, I think when you come back to funding, it's who's got the stomach for that type of time horizon.
I think the more difficult thing is the ability to capture value, right? So Varda is actually a company. So for people who haven't seen the news, by the way, Varda is a company that was recently announced that wants to create technologies for manufacturing in space. And there are various reasons why you might want to, manufacture in sort of low gravity environment. But the thing that's harder to fund, I think, is, long-term scientific research that where it's unclear what the long-term practical applications will be, if any, and or B, you can't patent a scientific discovery, right? You can't patent a law of nature. So if you don't have it directly tied to a mechanism where you can capture value, then it doesn't make a great candidate for a for-profit investment. For-profit investment has to get a return somehow, right? So if there's no way to capture value, then that is more of, that is something that basically needs to be funded through nonprofit, whether that's private or government. And that's basically how we fund research, right?
Yeah. Well, cool. So I have you for an hour and we're pushing up on that. So let's close with this. What is the ultimate goal here with Roots of Progress, which all listeners should subscribe to after they listen to this? But what's your ultimate goal here?
Thanks. Yeah, the Roots of Progress is my website, rootsofprogress.org, where I write essays about the history of technology and the philosophy of progress. What is my goal? Well, my first and most basic goal is I just want people to be aware of and appreciate progress. I think, it's not focused on in the world today. It's not really taught in schools. It's not commonly portrayed in movies or music or media or journalism. I think and so I think so many people are just unaware of how far we've come, how much the human race has actually achieved, how much better life has gotten. I mean, to come back to the beginning, the example about how excrement was just a part of daily life. It was on the streets of cities because horses, horse manure was on the streets of every city before we had streetcars and then automobiles. It was used as manure on farms before we had, synthetic fertilizers. It was sometimes even collected from the cities in order to transport back to the farms for manure, etc. It was kind of all around. We would even, if there were even deposits of bird droppings on these particular islands off the coast of Peru, where that made really good fertilizer and had been accumulating. They were like stories tall, and they were literally mining it like it was some sort of a mineral. It was limestone or something, right? They were mining guano. So, I just think the past is just horrible in so many ways. And people don't have the memory for it. We as a society don't have the historical memory for it. And so we've forgotten and we just don't appreciate it. So that's like the number one thing I want to do, awareness and appreciation. To my mind, the best possible outcome that could come out of my work is that the scientists, engineers, and founders who are, working on the next breakthrough today, or are going to, maybe the young people who are going to do that in the coming decades, if they can draw inspiration and courage from the stories that I tell and be motivated to go work hard and make those breakthroughs, then, I feel like that's the best possible impact I could have on the world.
That is awesome. And those are, I feel like those stories where, somebody impacts somebody else and they, maybe it happens 10 years down the line or, somewhere in the future, and you just can't connect those dots. Those are actually, some of the most impactful ones, especially when you're putting stuff out onto the internet and you don't know who's reading it or what they're doing with it. But I think it's great. So rootsofprogress.org. And where can they find you online on Twitter, or is that the best place to find you as well?
Yep. Yeah, so I'm on Twitter. My handle is Jason Crawford. And then you can sign up for my email list at rootsofprogress.org.
All right. Thanks, Jason.
And there you have it. That's the second interview of the Narrative Monopoly podcast. That you can find Jason Crawford on Twitter at Jason Crawford, Roots of Progress on Twitter at Roots of Progress. You can go to rootsofprogress.org. Highly encourage you to subscribe. Also, there is a Patreon button if you are feeling especially generous after listening to this episode. Otherwise, I will see you next week. We have a big episode with Ben Hunt, who writes Epsilon Theory. Really knowledgeable guy. Also someone who has studied narratives for a living. So please be sure to subscribe so you make sure that you catch that conversation with Ben. And if you are feeling extra generous, leave us a 5-star review with some words of encouragement as well. And please share with friends. We'll see you next week.